Hey guys, today's video is going to be solving exponential equations. Okay, so when we talk about exponential equations, we are talking about something like this. And so, in other words, it's trying to figure out what value of x makes this equation true. So pretty basic stuff, hopefully. Well, we're going to talk really briefly about three methods, but we're going to focus on one algebraically that I'm going to recommend for most problems. Okay, so one method that we've already done is by graphing these each as a function. This is a function, and this is a function, and then finding where those two graphically intersect. So if we took our calculator, we plugged those in, we pulled up our graph, scaled appropriately, and then this would be our solution wherever this is. And so it's easy to find on our calculator. And so it looks like our solution is x when x is negative 3.34-ish, like that. So if I were to plug that into here, so if I were to take 0.41, raise it to negative 3.34, my output would be this. So pretty easy, not particularly hard. But let's now do it another way. And this way we're going to use our new toy, logarithms. Okay, so with a logarithm, remember a logarithm is an inverse operation. Like in all our other parent functions, when we're solving for some unknown value, we use an inverse operation, and it's no different with this. Okay, so we're going to rewrite this in log form. So remember how we do that. So just rewriting this in a log form, we're going to start with, well, it's going to be a log. What's our base? 0.41. Now remember how we do that. We say base raised to the power of x returns this, our argument. Okay, and if you look at that right now, we're done, right? We've got x alone, we've isolated this, and if you look at this, you may not recognize this right away, but that's just a number. I mean, it's like a number like 5 or 4.5 or whatever. It's just we just have to pop that into our calculator. So if we do that, we get the exact same answer that we did graphing it. So, wow, pretty easy. But there is an annoyance in this problem here, and the annoyance is this guy here, dealing with this base on some calculators. Depending on your calculator, that might take, pushing buttons, going into different menus, and all sorts of stuff. So let's learn an even easier and faster way. Okay. To do that, what we're going to learn is the most important property of logarithms. And I should really say most important in my humble opinion. Okay. And it'll be a property, or actually a combination of properties, to be honest. But it's something that we're going to use quite a bit. Okay. So let's just take a look at this log in this form here. And of course, this tells us our base, and this is the argument. Okay, this here. Now, if I take the argument and raise it to a power, we can now re-represent this. And when I say re-represent this, we can rewrite this. And remember, this has to be an exponent onto the argument here. We can rewrite it like this. They are completely equivalent. In other words, this power is going to go down and then just be a factor. So in other words, these two are completely equivalent. And we really try to avoid actually ever writing this argument as a power unless we need to. But we like to just bring this down and express this as a fraction. Okay. So we call this the power property of logarithms. So take a second and just write down this property. Okay, so grab your calculator real quick. This is a TI-84. But if you're whatever calculator, almost certainly it's going to have these two buttons here. If you see me, these highlighted down here. Okay. Now, what are these two buttons? Well, obviously there's going to be a log here, and notice that this here, right above it, that's its inverse, right? These guys are inverses of each other, so that means this is a base of 10. So you might look at this log and go, hey, there's no base on that log. Actually, there is. It's a base 10. We just commonly, think about this. We don't write that 10 because it's what we call a common log. Okay. Well, what about this down here? If this is a base, what the heck this is? Okay. Well, this is actually a number. It's a very important number. That number is 2.71828, blah, 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 on forever. It's an irrational number, but it's a very important irrational number. Okay, many people call this the Euler number, as it was kind of, I don't want to say discovered by Leonard Euler, and arguably the greatest mathematician in history. And this number is, you could make a really good argument that that's the most important irrational number that we know of, and more important than pi. I don't know, you'd have a good argument. Okay, so basically what we're saying is this here, and that's an ln. Okay, is just a logarithm with a base of e, this number. Remember, it's just a number. Okay, it's a real number. This one just happens to be rational, an integer. This one just happens to be irrational, and you'll learn later on the significance of this number. Okay, so this we call the natural log, because it really it represents the connection with a natural growth. Okay, and this, we usually don't write this whole thing. We write it like this. Okay, and this becomes very important, particularly in later math classes, and in particular in calculus. Okay, so what do we care about these? Okay, what does it have to do with this? Well, we're going to use that property that we just learned. So here's what I'm going to do. I am now going to solve for it. We already know what x is, but I'm going to solve for it now a different way. What I'm going to do is I'm going to take the log of both sides. Okay, now notice what I did. This is not a base 41.41 rather. This is just a common log. So if I take the log to both sides, I'm now going to use my power property. And this is just going to move over to here. And now remember, the whole thing when solving for x, I just want to isolate x. So I divide both sides by that log of 0.41. Now think about it. This point, these are just two numbers. I just plug those into the calculator directly. I don't have to search through any menus because they actually have the buttons right there on the front of my calculator. So you just put log 19.73 divided by log 0.41. Bada bing, bada boom, you got it. Okay. What if instead you use the natural logs? Well, this is a completely different animal, right? Well, yeah, it is, but if you do it, you're going to get the same answer. Okay. Notice what happens here. And again, we know this is the correct answer, was we've already checked it with two other methods. Okay, you could always check that by taking this, of course, and plugging it into here, and as we have done here, and we get that 19.73. Now, don't make the mistake of thinking that these two are the same, because they're not. Okay, the logs themselves aren't the same. It's the ratio of the log. Just like if I had, like 6/18 and 1/3, we know that these are equivalent, but that doesn't make 6 equal to 1, right? That's the same idea here. They are the same as a ratio, but not as an individual. Okay, so these, make sure you remember that these are not the exact same thing. Okay, so let's try some problems using our new skill. So write this down, and then pause this, and you try it. We'll be right back. Okay, so just like we did on our example, we're going to take the log of both sides. We take the log of both sides using the power rule. This is just going to come right down to here. We're going to divide both sides by log 2.5. We just pop that into our calculator, and we get an answer of 3.5-ish. Okay. Wow, that was pretty easy, right? Okay. Let's try one just a little bit harder. Okay, so please pause and try this one. Remember, use the skills that we're isolating for x to solve this. Okay, hopefully you're back. Well, we're going to do the exact same thing. We'll take the log of both sides, but remember, when we take the log of both sides, this is going to come down here, and it's a factor, right? Again, our whole purpose here is to isolate x. So I'm going to divide both sides by log 5.2. And remember, I want to know what x is, not x minus 1, so I just add 1 to both sides and pop that in my calculator. And we give an answer here. Okay, so remember, we're going to use that power property, but first thing we have to do is get this, isolated here before we go through and isolate that x. Okay, pause and give this one a try. Okay, hopefully you're back, and the first thing I'm going to do, I want to isolate this first. So the very first thing I'm going to do is divide by 3. Once I divide by 3, I now have this in the position that I want. So I'm going to take the log of both sides. Okay. Now that I have the log of both sides, I have my x down here, so I need to isolate it. So I'm going to divide both sides by log 2. but also by 5. So I'll get to here, and again, this is just a number. We just plug that into our calculator, and we get this. Hopefully you're doing okay so far, right? Let's make it just a little bit harder, okay? So please pause and give this a shot. Okay, so we're going to do the same thing. Take the log of both sides, which is going to bring down my exponent. Going to divide both sides by this. Again, now we're just going through an algebraic process. Don't get intimidated. Remember, this is just a number. I mean, it's like 7. If this number was 7 in this equation, well, what would you do to get x alone? Well, now you'd add 3 and divide by 2. Well, that's what you're doing here. You're just adding 3 and dividing by 2. And that's what we get. All right, another one. Give this one a shot. Okay, well, here we're just combining more steps, right? Dividing by 8, take the log of both sides, and you'll see there's kind of a rhythm to this, right? Once you get this alone, the exponent comes down, divide both sides by the log, and then just do basic algebra to get x alone. In this case, we're just subtracting 4. And we get this. Easy peasy. Okay, now pause, and I want to say something real quick about this problem. Is in math, at least in higher math, which I would consider you guys at this point starting to get into higher math, this is not a variable. Typically, 99% of the time, when you see this e like this is the natural number. Okay, so remember that. This is just a number. This is not a variable. Okay, so pause and try this one. Okay. In this case, because we already have this as a natural log, so you have a button right on the very front. So here's what we're going to do. We're going to take the natural log of both sides, do just like before, bring that in the exponent. Notice we have done nothing different. The one thing that makes this even easier is because, well, this. Remember what a log is? Remember, this is log of e. This raised to what power is going to get me back e, right? Well, it's 1. So this is just 1. And at this point, we just add 2, and we have our answer. Okay, let's go for the big one. Okay, please pause, read this problem. This is something that we've done before, but now try to solve this with logarithms. So please pause and give this a shot. Okay, so hopefully you went through this problem, read through it, and recognize this as a sort of problem before. For us to answer previously, we had to graph this, but now we don't have to. Okay, so if you read through the problem and you set your exponential equation correctly, and you have your initial value, your rate of decrease, and all this sort of stuff, and you set it up correctly, you should get to here. Then our question basically becomes, how many years you're solving for this value of x until the population drops below 600. So that would be our output, which would be here. So here's the equation we're solving, and at this point, we just use logarithms. So first thing I'm going to do, divide through by 2400, and then take the log of both sides. Just like we did on our previous examples, we just use the power property, and it gets us to here. And what does that mean? 10.8 years. Okay, so this makes it fairly quick to do this versus playing around on your calculator, playing with the window and trying to get it just right for you to be able to calculate it graphically. But this last one, how many years ago? Okay, so again, we're solving for this x, and this is the output of our function. And now we're solving for x. Again, nothing new. Divide by 2400, take the log of both sides, and we get here. Of course, that means 11.2 years ago. So anyway, I know I went through this pretty quick, but I wanted to try to keep this video reasonable. So anyway, you guys, I have a worksheet for you. So go ahead and complete those. All the answers are posted. So I will catch you later. Bye.